Welcome to a video on the monostable circuit. We're going to look at applications, working principle, derivations, do a problem, then a simulation of a monostable circuit. So a monostable circuit is basically a trigger circuit. You insert a pulse of a sort and the circuit will switch on the output for an extended period of time. Okay, so typically monostables are used in timing and delay circuits, like those outside lights that switches on when they detect movement and then switch off after a minute or so, as an example. Then triggering and debouncing applications, when you have push buttons, they sometimes create a bit of oscillation, and you can use one of these monostables to debounce a switch. It can be used for pulse regeneration or for worn out pulses, meaning if you send a pulse over a long distance and it goes through a bunch of repeaters, the signal can degrade. So instead of just putting the pulse through a Schmidt trigger or something, you can extend the output or the signal to its original state. It can also be used as a temporary memory element. So if a trigger happens somewhere, the state of that trigger can be kept for minutes, hours, even before it auto resets. It is also used in signal synchronization circuits. For the old TVs, you have a horizontal and a vertical synchronization signal, and you can use a monostable to trigger those. So let's have a look at the working principle. As we know, it produces a square wave output on a trigger input. So we will insert a trigger and the output will happen for an extended period of time and then switch off. Okay, so basically we have a system with one stable state. Okay, mono means one. So the system can be resting here in the stable state. We insert some energy, pushing it up the hill, and after a time it will roll down again. Okay, so the trigger being the energy, and this extended period of time is before it becomes stable again. Okay, so it uses a diode clamping circuit on a astable multivibrator, basically turning it into a monostable. So basically eliminating one of the unstable states, or one of the stability states, sorry. And the RC circuit of the astable becomes the time constant now. Okay, and for the triggering circuit, we will be using a bit of a high pass filter setup. So let's have a look at the circuit. The trigger, the place where you take and pull it low to trigger the circuit, is up here, and the output down here. Okay, so if we insert a trigger, this is basically a quick happening or a discontinuity, and the discontinuity will pass through the capacitor, but the DC will not. So what you will see on the other side of the capacitor is basically the discontinuity, and the capacitor will charge back up again, and on this positive edge here you will have it going up and down again. Okay, so this is the high pass filter kind of input what you will get. Diode D2 here ensures that only the negative half of this pulse goes through, and if this is pulled negative on this side, this trigger here will go to a low state. So basically we will force our astable into a low triggering point, and suddenly this capacitor needs to charge up again from its stable state. Okay, so C1 and C3 is for our timing mechanism. This diode here changed our astable into a monostable. R1 and R2 is our feedback factor, and this up here is our triggering element. So let's look at the waveforms. So the red signal is the input trigger, and here is the positive and negative of the discontinuities. Okay, so basically with the discontinuity, a low trigger point is forced. You'll see here at the positive half, nothing happens here. Okay, so that this is eliminated using that diode, or else we will just force our circuit back into a high state. Okay, and we don't want that. So then after a period of time, we will go back to our high trigger or our high threshold, and this is when the pulse is complete. Okay, so basically changing from a high trigger level to a low trigger level, our capacitor was stuck at VD1 voltage level. Okay, so it will charge from VD1 down towards our L minus, but the triggering event will happen at VT low. Okay, so the period of time that we have here is what it takes. So charging from VD1, so this is V0 plus, charging towards L minus, so that is V infinite, and the voltage at time t is our VTL. So this is all the information that we actually need to use the capacitors charging and discharging to determine our signal's time. Okay, so just from input to output, we can insert a trigger. So from 10 volt, pull it down to 0 volts, and our output will go to low until the time has run out and go back up to L plus, and it will remain here until there is another external trigger. Let's have a look at the math. So the voltage at point B, let's go up here. Point B is our capacitor's voltage. Okay, so we want from V infinite minus V out plus, or V0 plus, e to the minus t over tau. Tau is the time constant of R3C1. We're charging towards the negative limit from the diode voltage, and the voltage at time t is beta L minus. Okay, so this will bring us to an equation that looks like this. Now, basically, if our limit, our output limit, is much larger than our diode voltage, this equation can reduce to R3C1 ln 1 over 1 minus beta. And remember, beta is our feedback factor, so the ratio of resistors. And for the input capacitor, we work this out based on the minimum pulse length of the discharging of a capacitor takes 5 time constants. So if you know how long the trigger pulse might be, you can fit this and calculate like a a capacitor and a resistor up there basically. Okay, so time for a problem. Design a monostable to create a 1.1 second delay. You have a 100 microfarad capacitor available for C1. The triggering pulse will be about 100 milliseconds and use a 1 microfarad capacitor. Okay, so we have a value for C2. Right, assume that we have rail voltages of plus minus 10 volts. Op amp saturates 1.5 volt, diode voltage 0.7, designed for a beta value of 0.5. When you're done with that, simulate the problem and see what you come up with. Pause the video and I will be with you for the solution in a moment. Right, for the beta values, we can choose the two resistors the same size, pick a 1 kilo ohm resistor, and our beta of 0.5 is satisfied. Okay, the higher you choose these values, the less current is consumed by your circuit. Always remember higher resistors, less current. But I'll show you in the simulation why I go with 1 kilo ohms. Okay, positive and negative limit is 8.5 volts, and our triggering points is at 4.25 volts each. Looking at our limit, 8.5 is more than 10 times larger than 0.7. So we can use our approximation and we get 15.87 kilo ohms. And I chose to put in a 15 kilo ohm resistor there. For the input capacitor, our 100 milliseconds will be equal to 5 times R for C2. And we will get the 18 kilo ohm resistor. So that is it for the design. Let's hop over to the simulation and see what happens. So here is my simulation. 1 microfarad, 18 kilo ohms. 1K, 1K, 100 micro, 15 kilo ohms. I use the plain signal diode here. You'll notice that I added the extra capacitor in here. I'm going to remove it. I'll show you what that is for in a moment. Always ensure that this resistor here is much greater than these feedback resistors, or they are going to start to influence one another and create some strange offsets. Something I picked up while playing around with this, and also this capacitor right here. So let's run our simulation. Here is our trigger of 100 milliseconds, and there is our output, right to the limits that we calculated. And from 100 milliseconds to 1.2 seconds, so this is roughly 1.1 seconds long. Okay, let's have a look here. We have our trigger, then we have our switching, and you can see that this already went back to 0 before the positive pulse happened. So let's make this a larger value. Let's say that's 100k, and see what happens here is you have your pulse and you have this strangeness going on here. So that's one problem. Or if you make this too low, you will have these strange pulses and you will have more noise or very large spikes translating into the rest of your circuit. So try and keep that kind of nice and low. Okay. On this threshold here, you'll see this spike. And this spike, I'm not a fan of having spikes. They create noise, goes into other circuits. Adding this capacitor right here smooths that out. Okay, so it's just basically a low pass filtering effect by adding a capacitor over this resistor right here. Okay, the charging of this capacitor, see it's a diode voltage, and when it charges towards the limit, when it reaches the triggering point, it switches on. This is at 4.25, and then it gradually returns to this zero point 0.7 volts. This time here is called the recovery time, and it's best not to have any input pulses before this has settled again, or else this time here becomes a bit unpredictable. Right, thank you for watching a video on the Monostable.